Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 13th, 2026, exactly 1 week ago. It introduces a unified family of open-source models that integrates perception, reasoning, and planning, significantly outperforming existing systems across 20 embodied benchmarks. The paper is titled RynnBrain, Open Embodied Foundation Models. And as we'll see shortly, the way it bridges high-level reasoning with low-level physical control is quite significant for the field of robotics. And for those interested in the implementation, the authors have shared their code on GitHub. On Hugging Face, you will find the 2 billion, 8 billion, and 30 billion parameter model weights, plus inference code and cookbooks for navigation and spatial understanding usage examples. Figure 1 illustrates the 4 core capabilities that define RynnBrain. In the top left, the cognition module handles standard tasks like counting objects or identifying materials. Moving to the top right, the location panel shows how the model predicts precise coordinates for affordances and trajectories, which is critical for physical interaction. Finally, the bottom sections on reasoning and planning demonstrate how the system interleaves these spatial tokens to guide a robot's actual movements step by step. So, Figure 2 breaks down the architecture that powers those capabilities. At the bottom, we see the input layer, which processes OmniVision data, like single images, multi-view feeds, and video, along with text instructions. These inputs feed into a central decoder, shown in the middle, which can be a standard dense model or a mixture of experts. Finally, the top section reveals the unified output space, where the model generates not just text, but also specific tokens for regions, trajectories, and pointing signals to physically ground its reasoning. Alright, moving to the training setup. Table 1 lists the exact hyperparameters used for pre-training. The foundation rests on the Qwen 3VL Instruct series, scaling from the 2 billion parameter version on the left to the 30 billion mixture of experts model on the right. While they use the AtomW optimizer for all three, the global batch size doubles to 1024 for the larger variants. The learning rates are kept conservative, around 2 × 10 to the -6, which ensures stable fine-tuning. So, Table 2 details the data mixture used to train RynnBrain, totaling nearly 20 million samples. The general multimodal large language model section at the top contributes 4.8 million examples, drawing from sources like Lava and shared GPT-4o to maintain general visual capabilities. But to build an embodied mind, the authors heavily weight the cognition and localization categories in the middle. These sections include millions of samples for tasks like spatial understanding and egocentric, or first-person task analysis. Finally, the planning row at the bottom integrates manipulation trajectories from datasets like OpenX embodiment, directly teaching the model how to move. Well, Table 3 presents the performance results for models under 8 billion parameters. It organizes benchmarks into embodied cognition at the top, location in the middle, and general visual understanding at the bottom. Focusing on the RynnBrain 8B column, we see it consistently outperforms the base Qwen 3VL model and competitors like RoboBrain 2.0. For instance, on the spatial reasoning task versus SI bench, it scores 71.0, which is a clear jump over the base model's 60.3. Okay, Table 5 focuses specifically on physically grounded reasoning. This comparison pits the RynnBrain chain of point variant against major competitors like GPT 5.2 and Gemini 3 Pro, all evaluating with thinking modes enabled. As the highlighted bottom row shows, RynnBrain dominates every category, securing a 90.3 in affordance and a 71.2 in trajectory. This results in a leading average of 73.8, which beats the much larger proprietary models by a clear margin. Wrapping up, 2 takeaways stand out. First, RynnBrain successfully bridges the gap between high-level reasoning and low-level physical control by integrating spatial coordinate tokens directly into the language model. Second, the release of these open-source models offers the community a robust backbone for developing agents that understand real-world physics, not just semantics. Together, these advances bring us closer to truly generalizable, embodied intelligence. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.